Hi, everybody. The goal for today is going to be to cover two sections from the F book 1.3, which is about relations and functions, and then 2.1 about the beginnings of logic. And this is going to be in two segments. So let's get started on the relations and functions stuff. First, I want to mention something that you probably have heard of before. Infix notation versus prefix, or there's actually even postfix notation for mathematical operations. Like if you write 1 plus 2, that's infix notation. The operator goes in between the two things that are being operated on. Prefix notation would be something like, maybe you had a function called add, and it would take 1 and 2 as its arguments. And so it would be the same thing, but I don't know if anybody would anybody ever write plus and then 1 comma 2? Same idea, just putting the operator out front rather than in between. And some functions, functions almost always have this kind of form. Functions and their generalization relations usually have these things. Well, one does the infix and the other does the prefix. So the definition for relations is actually very abstract, but you know lots of things that are relations. So whenever you begin talking about relations, I want you to think about the less than sign. And if you're going to think about a function, then I guess I could say I'll pick a particular function. Like think about squaring. Think of f of x is equal to x squared. If you want to imagine a function. In other words, these are sort of prototypes for the two kinds of things. In what sense do I mean that? Well, if you have a is less than b, what kind of entity is that? Versus if you have f of x, well, how about f of something concrete like f of 2? Well, a is less than b is Boolean. It's either true or false, right? It's the sort of thing you could use in the condition for a conditional execution thing, like the if statement. If a is less than b, then make it bigger, and it'll be. But f of 2, this is a function with its input supplied. That's not a Boolean. That's got a value. Actually, it's a real number, I suppose. Depending on where we're thinking about the function living. It could be a natural number or something too. If I tell you that f of 2 is uniquely defined, you'd probably agree with me. If we're actually thinking about x squared, f of 2 is 4. Right? And there's just the one number, 4, that goes with 2. But if I had the less than symbol, are there other numbers that work with 2? Could I have 2 less than somebody else over here? Yeah, lots, right? There's tons of things that are bigger than 2. So for a function, the input uniquely determines the output, but for relations, that's not the case. You could have lots of a's, you could have a and then lots of different b's, or you could have it vice versa. Pick b, make it set, and then have lots of different a's that are smaller than it. So that's the major difference, this uniqueness of output from the function, and no such thing with relations. Now there's a definition on page 16 in the book that I'm going to have us look at, and we'll go to the screencast for that. Right, so here we are looking at the scan of the textbook. I can't see what page we're on. It's page 16 of the scan, but where is it in the actual book? There we go. Page 16. How about that? Page 16 in the scan matches with page 16 in the actual physical book. Anyway, this is where you see a definition. Watch out for these kind of things in this textbook and in most math books. They're really important. When they give a formal definition of something, usually they mark it off in some special way so that you can quickly locate it if you're scanning back through the book. So in this book, they put a box around them and write definition and have this big blue header for it. It's important because when you're making arguments about things, it's important that the things be well defined and that everybody who's talking about them has the same notion of what they mean. So, what do we have here? The definition, the term being defined is given in bold here. Oops, I can't really highlight anything, but there it is. A relation R from A to B. That's what's being defined. That means you've got a setup here. A and B are sets. A relation R from A to B is, well, it's a subset of the Cartesian product, A cross B. The next sentence is just giving us the definition of how to talk about things being in the relation. Like I said before, you should imagine the less than sign as kind of the prototype for what a relation is. So how do you talk about, 3 being less than 5? You say X is related to Y by the relation R, or just X is R related to Y. That's another phrase that you can use there. And you write XRY. That is, the R symbol goes right where a less than sign would go. It's just stuck in between the two things that are related this way. That's the infix notation I talked about before. So X is R related to Y if and only if, now we're getting to the real point, X comma Y, that's a pair, a thing from A and a thing from B, if X comma Y is in the set R. So in other words, this second sentence here is giving us a way to sort of have a shorthand for when two things are related. You can, the gold standard is the pair XY is in the relation, but a shorthand for that is XRY. Now the rest of this definition includes some definition of terminology. You've run into the domain and range before when you talked about functions, but now we're talking about relations. So the domain is the set A. What we normally think of as range is the stuff on the right-hand side, but that's not quite right. So the set B is actually just known as the codomain. We'll talk about range in a second, but right now that's the codomain. I don't see any difference between what they've written in these two separated out sentences and what they had up here before. See how it said before X, R, Y, if and only if X, Y is in R? Well, the only difference is up here they use the word in, and down here they use the symbol for in. I guess that's a slight difference, but really that's the same. I guess the real point of this second pair of little sentences in our definition box is to get at the notation for not being related. So, we had less than. What's the idea of putting a slash through less than? Actually, we have a symbol for that. It's greater than or equal to, but if generally you can write less than with a slash through it too, not less than. And we similarly can put a slash through an arbitrary relation symbol R. So if the pair XY is not an element of R, then you'd write X slashed out R, Y. All right, so when we're in that scenario where a relation is defined abstractly as some subset of a Cartesian product, and what we just came across in that definition is that R is just some arbitrary subset of the Cartesian product A cross B. So R consists of a bunch of ordered pairs. And you say that an ordered pair is in the relation literally when it's in that set. And it's not in the relation when it's not in that set. So you have a pair A comma B is an element of R. The way you say that AB is in the relation. I guess I should, whoa, that was weird. I just was starting to think about parentheses around these guys, and they need it. But what I need over here is the end quote to match with that begin quote. The pair AB is in R, so that's how we sort of think about it in terms of that set of ordered pairs. But there's a shorthand you should know, and it looks a little weird, I gotta admit, but this is what you write as shorthand. you put the letter R there in sort of the same position the less than sign would go. Remember, our prototype for relations is the less than guy. So the shorthand is to write A, R, B. And I would say that A is R related to B, is one way to put it. You know, different symbols could go in between here. Many relations have known symbols for them, the less than sign, greater than or equal sign. The equal sign is actually a relation too. But if you don't have a known symbol, then you just call it something, and then you use that something is the thing that you stick in the infix position between the two things. If you want to say you've got a pair that's not in the relation, of course, the set theoretic way to write it would be that the pair AB is not an element of R, not in that set, that subset of the Cartesian product. You can do a similar strike through like we do with the element sign. So the shorthand notation for that would look like A, R, with a slash through it, B. And you read this, A is not R related to B. Okay, there are things to describe relations that are called arrow diagrams. Some people call them sniper diagrams, that'll come up more when we're talking about functions. So let's make up a random abstract relation, and then I'll show you what its arrow diagram looks like. Well, to make up an abstract relation, I first need to specify the sets involved. What are the A and B in that Cartesian product? So how about if we have A be the set of numbers 1, 2, and 3, and B will be the letters A, B, and C. And so A cross B has 9 things in it, right? And I'm going to make R be some subset of that set of 9 things. The R is going to be equal to, what shall we have? How about 1A, 1C, 2B, whoops, I forgot the first paren, and I don't know, how about, well, that's enough. Heck, just 3 things in it. Now, I feel like I would love to have one more thing in it. How about we throw 2C in there as well? Okay, so what's an arrow diagram look like? What you basically do is you make a Venn diagram with A on the left. So you do a big circle with the elements of A in it, which would be 1, 2, and 3. And on the right, do a similar thing for B. It's A, B, and C now. And if a pair is in the relation, then you draw an arrow from the x coordinate to the y coordinate, that is from the left-hand side to the right-hand side. So 1 goes to A, and also 1 goes to C, 1A, 1C. 2 goes to B, and 2 goes to C. Well, that's an arrow diagram for a relation. I guess I should point out that if we had a function here, well, one feature of this would just tell us, no, that's not a function. If you thought this R might be a function, because functions are going to be defined in a second as relations that have some additional properties on them. So you start with a relation, you put some restrictions on it, and you get a function. But this is the kind of thing that breaks the thing. It makes it not functional. Where 1 goes both to A and goes to C, that's not okay with functions. Input should go to a unique output. You can't have this idea of splitting. So diverging arrows in the arrow diagram, arrows that start at the same place and go to 2 different places, not allowed when you got a function. But converging arrows like this, that's perfectly fine. Like, you probably know that if I square 2, I get the same result as if I square minus 2. That would be 2 different things that go to the same result. So that's legal in a function, but we can't have the same input going to 2 different outputs. All right, so I just said I was going to talk a little bit about the definition of function, or how you write a function as a relation with additional conditions on it. Let's move over to the screencast again, and we'll do that. Right, so I wanted to now talk about functions in the context of functions as being a sort of relation. The definition that appears in that for that is on page 18 in the textbook. Down halfway down the page, it shifts to talking about functions, sort of a new subsection, and then it gives this definition. I'm just going to read it to you. A function f from a set A to a set B is a relation, and the domain is A and the codomain is B, that satisfies the following two properties. For every element x in A, there is an element y in B such that xy is in the f. Xy is in the function. That is, x is an input that gives you y as an output. What is that really getting at? Every single element of A has an output that goes with it. So you can see some arrow diagrams up above. Now, these are both not functions, but notice on the one on the left, everything on the left side has an arrow that leaves it. That's that condition. This would not be a function for two reasons, actually. One is this doubling, splitting of an arrow, but the bigger one, the more obvious one right now, or the one that's relevant to property one here, is that 1 and 3 don't have anybody to go to. Everybody has to have somewhere that it heads to if you're talking about a function. Every x has to have a y that goes with it. The other condition is a little tougher to talk about. For all elements x in A, and I like to use numbered ones, y1 and y2, but they've got y and z here in the book. If xy is in F and xz is in F, then y and z are actually equal. What that's getting at is what I just showed up there on the diagram before. But let me give you an example of this, or write an example of it. Suppose we have the numbers 1 and 2 on the left side of an arrow diagram, and the symbols A and B on the right. Sorry, let's call that set B, and this one set A. And I want the points A and B to be elements of set B. Okay, that is a very ugly looking B. I'm trying to fix it, but I probably never will. Okay, so what would something look like that failed to have this second property that's there? It would be something like this. One gets sent over to A, and at the same time, it gets sent over to B. So A and B here would be the things that are called Y and Z in the definition. Two things where one A is in the set, or is in the function, and one B is in the function, but darn it, A and B are not equal to each other. What would it say to you if we had what happens in that bullet 2 there in the definition? It would mean that these guys were really the same, which means we shouldn't have drawn it as a second arrow or a second point. This guy should just be pushed over until it's right on top of A, and then you erase the B. Excuse me. So, yeah, that's not really there if you've got a function. There's one arrow that goes from 1 to A. Because, well, I get that this seems like a strange way to say it. What you really are trying to get at is you don't have any pair of pairs that share the same x coordinate. But this is a condition that guarantees that to happen. And, well, frankly, it's very easy to use in certain circumstances. So while it's maybe not the clearest way to get at the idea that arrows don't diverge, which is physically what's happening, it is very easy to use when you're trying to prove something about a function. I did want to mention a couple of things about the arrow diagrams when we do have functions. So suppose you've got an arrow diagram with three things on the left and three things on the right. This is set A, this is set B, and this is going to be a function that goes between the two sets. So what are my conditions about being a function. The one that's over here, the first one says for every element in A, there's an element in B that's associated with it, so that that pair is in the function, which means every spot over here has an arrow leaving it. If you talk about sniper diagrams, I hope nobody has PTSD because this is a little bit weird, but sniper diagrams means, or an interpretation of that is, if you've got a squad of 3 guys and you're planning to shoot at your enemies, everybody shoots. So that's what problem, oh, under the guise of sniper diagrams, that's what number 1 would be written by. Everybody's got to have an arrow leaving them, and I don't care where they land. You might have everybody shoot, well, the top guy shoots the one in the middle, these two both shoot the same thing. There's an arrow leaving everybody. That's the main point. Now, what does this other thing mean? That for all elements x and y and z in B, x and a, y and z in B, if 2 different pairs are in F with 2 different y coordinates, then it turns out those y coordinates are actually equal. That means that you don't have, so 2 means this doesn't happen. Well, how would you say that if you were talking about people actually engaged in warfare? No, everybody should be firing 1 shot. Nobody should have multiple targets, and that's probably good practice, right? If you really think about people who do this as their job in the armed forces, you want to shoot once and get out of there. You want to hit your target and then go to safety, because once you've fired a big loud gun, people probably are going to notice where you are. So having to stop and shoot multiple targets, and it takes you a little while to change targets. So I guess I would say this colloquially as no multiple targets. Now, is that really the case with snipers? I sort of doubt it. I think in the heat of war, people do need to take on multiple targets, but ideally you wouldn't have to do this. So, yeah, so that's one way to think about these issues for functions. The everybody shoots idea says that the domain of the function is actually it agrees with what we would call the domain of the relation. That is, it's the entire set A, and the no multiple targets idea is that, well, that strange 2 property that basically we don't want to have arrows emerging, more than 1 arrow emerging from any input. Each input should go to a unique output. All right, so we just got through making this sort of definition that F is a subset of A cross B, that is, it's a relation, but it has some additional conditions on it, that if a pair x comma y is in the relation, let's call that x comma y1 is in the relation, well, the relation is this function f, and x comma y2, that's in the relation, that's in f. So if those 2 things are both true, then it turns out that we're actually sort of mistaken about these things being different. This is how we actually make the uniqueness happen. Y1 actually has to be the same thing as Y2. So it's sort of a weird way to write it, but it turns out to be useful when you're making arguments. If you had x go into 2 different places, you're just wrong about that. Those places are the same. Yeah, so that tells you that the output that goes with any input is unique. The other thing that we had to have was that every element of A appears as a left-hand coordinate. That is, the domain of the function is all of A. But I'm gonna leave that. Well, we just did that. Shorthand for this, because that really does look strange to talk about a pair being in a function. That when we say x comma y is in the function f and bears this relation to one another, we usually write it this way: that f of x is equal to y. So the relation notation when it's a function is different, and this is notation that goes back to Leonhard Euler. So if you need a name for that kind of stuff, it's called Euler notation. The famous f of x notation. I did want to point out a funny situation, not unusual, but a situation that happens fairly frequently when we've got a function that is a subset of a Cartesian product. Quite often the two sets here are actually the same thing. So I'm going to speak generally about relations rather than about functions. You've got a relation that's contained in A cross B, but that relation could be a function. I'm just writing R because I can say things about both functions and relations at the same time now. When A is equal to B, and when it is the two sets are the same, that means R is really a subset of A cross A. If you like, sometimes people will denote that using a power, right? A squared is the set of things A cross A. In that case, the terminology changes a little bit. Rather than saying, let me review. Well, actually, wait, I never said this in the first place, so it's good that I'm doing this now. I'll give you the language for talking about that setup. Rather than saying R is a relation from A to B, which is when A and B are distinct from one another, rather than that, you say R is a relation on A. Oh shit, I left the word A out of that. So, for instance, I could say the squaring function f of x equals x squared is a relation on the set of real numbers. It's also a function on the set of real numbers. So everywhere where I said relation, you could replace that with function and maybe make the r's f's, and it would be the same change in terminology. When are functions or relations equal to one another? Equality is it's sort of a generic issue that you have to deal with when you're doing math things. Sometimes the very same object gets presented to you in different ways, and you need to go, oh, that's just a hidden version of the same thing. So I'd like to know, how do you precisely say when two relations or two functions are equal to each other? And probably the best thing about this idea of defining a function or a relation as a set of ordered pairs is that it settles this issue. When are two relations, say R and S, actually equal? I guess maybe I'll mark this as a Q because I want to immediately answer what the A is. Both of these things are sets of ordered pairs. And sets are equal if they have identical entries. So they must be equal as sets. They have to have the exact same ordered pairs in them. Now, there are a bunch of a bunch of other sets, some terminology anyway about sets that are related to, and we have relations and or functions. So let's just put a little divider symbol in here. You probably, I know you've been told about these things. It probably comes up in like pre-calculus or even intermediate algebra. Domain and range, do you remember those terms? Domain has the Latin root word for home in it. So this is kind of justifiable. It's where the function lives. Which, to my mind at least, sort of makes sense. That this means the inputs. Well, that's a very ugly U. Let me just fix that one. Range, on the other hand, I think that's actually very clear. If you think about going to like an archery range where you shoot at targets, the range is the targets. If we're doing with an arrow diagrams, it's literally the things that have the arrowheads landing on them. So range is the outputs. So these sets, domain and range, actually have standard notations that come along with them. You can talk about dom of a relation R. That's the collection of all things that appear in the left-hand set. Or of course, if it's a function, you would say dom of F. And the range, you say RNG of R or F. We'll just add that we have the idea of domain and range for arbitrary relations as well as for functions. Yeah, there's also a third set wandering around, but there is not, for funny reasons, there's not a fourth set. Let me explain what I mean by that. If you do one of those arrow diagrams, let's go ahead and just abstractly talk about one of these arrow diagrams. You'll have the set A on this side, and the set B on this side, and there's a bunch of things in A, and there's a bunch of other things in B. Maybe some of them are the same. And you draw a bunch of arrows. So I'm just going to throw lots of arrows on the board. Just try to be abstract. How about this guy goes up to there? Well, there's a couple of things. There's three things in here where all the arrowheads are landing. Right? And then there's a couple of things that are not the image of anything. There's things that the function doesn't go to. That's not so strange if you think about, oh wait, is this a function? Yeah, this one's cool, it's a function. So I was thinking originally I would write a relation, but right now I've got a function. If I wanted to make it a relation and not a function, I could just add one more arrow that makes it break the vertical line test. It makes it have one input that goes to two outputs. But anyway, this set of things that have arrows landing on them, that's the range. I guess we'll call the function f. Oh, it's not a function anymore. I just messed it up. So gotta not call it f. Let's call it r. The set over here, if you're having a function, this is got to be the domain. That is, you can't have anything that doesn't have an arrowhead leaving it. But you do generically have this issue, that there's some stuff outside of the range. So the set B that contains the outputs is called the codomain, and that's written cod. This is all much, I wouldn't call it F again. This is all much more important when you're dealing with functions. So let's fix this by removing that one troublesome extra arrow I put in. Okay? Take that guy out just like it never happened. Now I've got a function, so I'm just for the sake, really a function could be named R just as well as anything else, but let's call it f now. So these arrows in here constitute what f is. The point is that the domain of f, if it's to be a function, has to actually be the set A. So there is no container for the things that are inputs that are valid. And this goes kind of contrary to our intuition, because a lot of times there are points in a function's domain, or what we think of as its domain, where the thing's just not defined. Like, can you take the square root of a negative number? Can you divide by 0? There's positions in what we think of as the domain that are disallowed. That just means we're wrong about what we think the domain is. See, the domain is, by definition, the set of valid inputs for the function. Okay, so if you say, oh, but we can't take square roots of negatives, it just means the domain isn't the real numbers. The domain is the positive real numbers, or I guess non-negative real numbers. I'm going to also now go back to the screencast to show you a little bit of a distinction there. But the main idea is going to be, we sometimes think functions are identical because they have the same rule. But there's more to that story. They gotta also have the same domain. Let's go over to the screencast and I'll show you. Okay, so finally we're going to talk a little bit about when functions are distinct from one another and when they're equal. Usually people just take the attitude that they're equal if they have the same rule associated. A function is often, well, at least when I was a kid, they defined it as a rule. I believe that now for you all, the new math influenced things, and they did probably early on make this weird definition we're doing now of saying a function is a type of relation, which seems really weird and awkward to me, but maybe it's good at this point because you'll be perhaps more used to this. So I've got Desmos up here, and I want to have it plot one of our favorite functions. How about y equals x squared? Fine. I could have exactly the same rule, y equals x to the second power. Okay? And those two functions are equal. But something that is often done with functions is we make a restriction on them. We just say, look, I'm going to square the output, or I'm going to square the input to get the output, but I don't want to deal with negative numbers. Would you be okay with me saying negatives are weird, I don't want to handle them? You can do that in Desmos like this. You put a curly brace down and you just write an inequality. I see x is greater than or equal to 0. And now you can tell that the red graph is this whole parabola, and the blue graph is just half of it. If I turn the red graph off, you're just getting half of a parabola. Now there's actually a good reason to do that particular thing, which it has to do with finding an inverse for the y equals x squared graph, which you guys know the inverse for the squaring is the square root function. And those are indeed inverses of one another. You can tell because they're mirror images in the line y equals x. I hope this is stuff that's familiar to everybody. You see how they look like they're just mirrored across that purple line? So what we do when we take to define the square root function as a relation is actually really kind of interesting. You have a function f, right? And you've got an ordered pair x comma y that's in it. Well, for the inverse function, that is, if this is true, then it leads us to saying that y comma x is in the inverse relation, or the inverse function. That's true for relations as well, but we usually think about it in terms of functions. That's why there's this symmetry. You're just interchanging the roles of the x and the y coordinates when you look at the inverse. That's how you get the square root. Now, if I interchanged the roles of x and y in the square root, in the squaring function without this restriction of a domain, let's turn this guy off, put that one back on, you can see that there are pairs that are in the function, like over here at whatever it be, that spot right there is, I can't seem to land on it here. I'll just type it in. -2, 4 is a point that's on that graph. What point do you get if you interchange the x and y coordinates of that? It would be 4, -2. And that red point is not on the green curve. So if we really wanted to plot in Desmos, you can do this. You can plot things that are not functions, which is kind of fun. If you really just want to get the inverse relation for y equals x squared, it's x equals y squared. Oops, to the second, right? That gets the whole thing. And all the pairs that are in red, all the points that are red over here, when you interchange their coordinates, become blue over here. But what's the problem with this blue thing? That's not a function. That fails the vertical line test. This has got the same input, like 9, going to both 3 and to -3. In other words, that's a sniper that's got to shoot 2 targets. So one of the principal reasons for restricting domains is exactly what we just described. If you didn't restrict the domain, you'd end up with a non-function for your inverse. Click that off. The restricted guy has a very nice, a thing that's a function and as its inverse. But there are other times when you restrict a domain. For instance, the algebraic rules might be broken at that point. Suppose you have a function that has division in it, and for certain values of the variable, you get division by 0. And you restrict the domain in that case so that the function is defined on its entire domain, meaning you eliminated those problem spots. So if you take the perspective of functions being relations, which are sets of ordered pairs, are these two things the same set of ordered pairs? Blue, red? No, they're not. The red curve has lots of ordered pairs in it that aren't in the blue curve. So these are not equalist functions. And the take-home lesson here is a function's identity depends not just on the rule, but what its domain is. When I say the rule, I mean something like x squared, which tells you what to do with the input x. You have to also talk about the domain. And I think this is one of those moments where you have actually seen notation all along that you didn't understand, and now hopefully you will get it. If I say something like y is equal to the square root of x minus 1, and then you see a semicolon and an inequality, something like x is greater than 1, could be greater than or equal to 1. That's doing what we're talking about. It's specifying the domain. And so y equals square root of x minus 1 with x greater or equal to 1, I've got a known value for the domain. But if I said y equals square root of x minus 1 and then specified x has to be greater or equal to 2, these guys have the same rule associated with them, but they have different domains specified. So they're not equal. The sets of ordered pairs, the top one has ordered pairs where the x coordinate is between 1 and 2, and the bottom one doesn't. So, all right, well, that's it for this portion of the lecture. I'm going to record another one about section 2.1 shortly.